Hello, Steve Grillo here. With this discussion, we will be drawing to an effective end of the diverse discussions that have been part of this extended assay. As we see here in front of us, this title, Spatializing Galilean Relativity Expansion, we're going to take the important structural points that were explored closely in spatializing Galilean relativity and give them some flourish to make what I think is a very innocent remedial beginning point in simple math space, and then expand on the important arguments that I have previously developed that show us how to look more carefully at schemas that are regulated by both non-inertial and inertial mathematics. So this will be a survey. As such, we can look forward to some insightful asides and hopefully telling considerations will emerge. So, this assay that I have puzzle pieced together began as a simple question posed in purest math space. In math space, for example, we can easily see that things perhaps don't follow any kind of normal and or provable truth. They simply are things we can explore, and our cognitive processes tell us if we have gone outside the norms of math themselves. But math is very plastic, and so it can do quite a number of exotic things, all in the context of itself. So, for a quick example of a math space exploration, we recall the 1960s, when the evolving quantum model was getting injections from notions produced here and about, one of which was the idea of a tachyon. The tachyon was an entity that presumably never fell to a speed slower than the speed of light. Now, that gives us a very concrete thing to understand about it, but it requires very simple, flat space to do so. We understand that if a photon and a tachyon leave Earth at the same time, the tachyon will certainly reach Mars well before the photon. Now, we do that with our inherent math processor, even without thinking about how far away Mars is. We just understand the dynamic. The dynamic is one entity is moving faster than the other. And we really don't even have to put any kind of quantitative conditions around the idea of the space between, as we say, Earth and Mars. But be that as it may, the concept of space has to be real, or you can't understand motion, because motion without space is a null concept. So, to describe entities like our tachyon and photon, we start in open math space and then add conditions. Here, we say that one moves faster than the other. But then we must ask if there is something about our cosmological space, as we have come to know it, that prevents the insertion of a tachyon. Well, we have never seen anything move faster than a photon, so if it exists, it must be very hard to detect. This leaves us hoping that one day it will be detected, but till then, it remains a tantalizing math space entity. We can easily see how it could map down onto our cosmological space, but for now, it remains hypothetical, an entity suspended in math space. Now, that's just a quick idea of how math space serves us. It is the true crucible that holds our conjectures, some of which are merely mathematically beautiful. Very few of us can get that far into that depth. However, as we turn to our case, what we will be looking at is a very simple time rate schema, very much like the tachyon and the photon heading to Mars represents. So speaking algebraically, we can introduce entity A and entity B and assign a high velocity for entity B and assign a velocity to entity A that is lower. We could separate them by some distance L, and then presume that at t0, entity B is going to travel straight towards entity A along A's path of motion, and at some point overtake it. Well, that's what we see here. It travels and it overtakes A. We see that A has left its origin and traveled through space some distance. And as entity A traveled through space, it got this far before entity B intercepted it here, T1. So we see X as the small distance the slow-moving entity A traveled, and by comparison, L plus X as the longer path that the faster entity B was able to manage. Longer, shorter. And our point is that both of these distances, given the two different velocities, are covered in the same time. And when we look over here, that's what we see in all of this expansion of the arguments in mathematical terms. We're seeing the reduction of the episode to a time. And we should note that this is pure math working for all intents and purposes in pure math space. We have not introduced any units of measure, so we simply have two entities in math space. We can say that they are entities without mass, without form. They are just notions. But we can do that abstract exercise, and this math will give us how X is achieved and so forth. Well, we can extend this case by very simply overlaying this particular scenario with a two-part frame, with distance L as the length of its members. Let's say the frame possesses a northern leg and an eastern leg. Each leg is defined by L. Let's say the northern leg separates at T0 and travels north at the low V of A, while the same entity B is then going to traverse the corridor of the northern leg as it moves. So we see exactly the same activity as before, just looked at in a slightly different way. We see X is the distance traveled by the frame as entity B traveled L plus X through space to get to the intercept point at the far end of the frame. Again, that would be T1. The same distances and time as in the first scenario. We simply see B associated with an entity we can call a frame. Whether or not the frame is considered a notion or a material thing is not important. The same math applies. Now here's where we could start seeing interesting asides. Notice that as entity B traversed the corridor, as indeed the corridor itself was moving, the corridor had 10 tick marks along it, whose gaps match tick marks on a given reference in space. As entity B traversed the length of the frame, we see that it passed by 10 tick marks, but it passed by more than 10 tick marks in respect to the spatial reference. So we see how relativistic assessments present themselves. Again, our expression calculates a ratio. We need x over small v and L plus x over large V to produce the same ratio. And as we know, when common physical values are inserted, that ratio comes to represent time. Now, it will serve our purposes once it intercepts the leading edge of the frame to have entity B reflect back down through the corridor. In doing so, it will be traveling in a new direction, namely south, as, of course, the trailing edge of the frame is still heading northwards. Frame heading north, entity B returning. And so, that distance traveled by entity B is shorter than the original L plus X. Its new run is L minus Y, where it is clear that this represents a shorter path. Y, of course, is the new distance the frame will travel. Frame being here, travels Y. So reversing entity B as the frame continues as before produces this expression. And taken together, we would say that entity B has traveled a cycle going here and then back. As we noted earlier, entity B traveled through all 10 tick marks that were inside the frame on its first leg of the cycle. In this reflection phase, it will do so again, but in respect to the spatial reference, it will pass by fewer than 10 tick marks. The external spatial reference illustrates a different count, but it is the proper count, for it properly informs the expressions at hand. Given our long-standing history of math, we see that these two episodes, there and then back again, for the high velocity entity can actually be stated this way, where the high velocity entity and the length L and the low velocity of the frame are all represented here. And when taken through this exercise, it gives us exactly the same total cycle time as when these two episodes are added together. These two episodes, there and then back again through this dynamical expression, reduced to this more sophisticated expression, gives us the total cycle time. These two cycle times are equal. These two operations, taken together as a cycle, yield a total time that is equal to this more sophisticated mathematical expression. Now that we have examined a simple activity, that is, a simple cycle, on the northern leg, this assay must now turn to the eastern leg and consider a cycle along it as the frame continues northward. We can see here the purest and simple exercise we can ask of this new condition. Now we're looking at the entity traveling eastwards as the frame still yet travels northward. And the simple breakout is, well, we see it here. Well, there goes the frame northwards, and there goes the entity eastwards. And very instantly, as they separate, they really don't have much of an ongoing relationship with one another in any real pure sense. They simply separate, notably, from a point in space that is the origin of this episode, and that's all you see. One goes northwards and one goes eastwards. Now, in keeping with what we examined earlier, which was a simple cycle, where the there and back again just created a bit of a mathematical condition for us to solve, when we impose the simplest requirement for each, i.e., the frame going northwards and the entity going eastwards, we see that we do not automatically have the makings of a cycle. The frame and the entity simply part when we ask them to engage with their simplest behaviors. Velocity east, velocity north. Well, we could impose an additional behavior onto entity B that puts it somewhere inside the north moving frame. So some northward jaunt has to be part of entity B such that it remains inside the frame as the frame moves off at its lesser velocity. So we can see that a purely eastwards direction for entity B does not help us build a cycle. Entity B must follow some northeastwards vector to have any chance of being part of a cycle. That simple stricture would put it here, somewhere inside the frame. But now we have to ask a very probative question, and that question opens onto the heart of this alternate assay that I'm trying to produce. Okay, we wish for entity B to somehow engage with the frame as the frame moves northwards. How? In other words, how much northwardness do we need to add to the entity? Well, we want to engage with the frame, but with what objective? Well, we want to cycle. Well, we want a cycle to happen, meaning we need to intercept the far end of the frame and reflect back. Now we have an acute dilemma. If we have freed the entity from traveling strictly eastwards, then can we allow it to have any of a variety of velocities that will create a reflection? To wit, if we slow the entity to 19 kilometers per hour, we simply need to find an emission angle that will satisfy a reflection. Further, if we slow it to 18 kilometers per hour, then we can find that emission angle, knowing it will be larger than the 19-kilometer angle, and so forth, until we reduce the entity to 10 kilometers per hour, where it must remain at the starting point of the eastward leg and travel directly northwards to remain in the frame. Conversely, if entity B travels faster than 20 kilometers per hour, the emission angle must be lower, and then you get lower and lower as the velocity of B increases, going faster to the outer edge and back. So this angle gets smaller and smaller as speed increases. So we see a huge range of solutions for a reflection to occur. And with all that said, we notice that for certain there is an angle that will recreate a reflection if we keep the entity at the original 20 kilometers per hour. Further, since we have our original high velocity and low velocity entities in play, then this alteration to the original equation gives us the time of that cycle. All we need to do is to add a radicand here in the denominator, and we get the total time of a cycle that has large V and small v as the standing roots. So we must trust this alteration to the math just as we trusted the previous expression. But why should we like this reflection solution? I guess because we've used the same values of large V and small v, just as we did in the northward cycle. But we make the venerable observation that this cycle time is not equal to the original cycle time. If the difference in cycle times is not meaningful, then why shouldn't we be free to pick any solution for a reflection? Again, we must say we simply favor the idea of using the same values for V and V. And while we ruminate on which reflection solution to use if unequal cycle times are acceptable, we face a much larger issue. I'm about to make a statement that I hope to clarify in the next segment. both of these cycles, northwards and northeastwards, are non-inertial in nature. The there and back again cycle on the northwards frame mimics the simple math-based episode of an entity overtaking another entity, so it doesn't draw too much attention to itself as being an inertial or non-inertial circumstance. But the east-northeast cycle, when we spatialize it, looks decidedly inertial, but is assuredly non-inertial. So there is much in that to be realized. We see the summary of these basic ideas here, sending entity B down a path where V is important and the frame itself is moving at small v and it's going down. And so we easily see that with the given values, we get an angle that reflects at the far end and returns to the base of the frame as it moved from basically here to here. In this segment, we add what seems to be the merest complication, but it opens many doors. Staying with the east-northeast cycle, we can say our previous assessment simply found the frame at T0 and began instantly to move it at V, just as we found entity B at T0 and instantly imputed larger V to its motion. Essentially, we found them co-located at a point in space and then began an exercise that linked them. But what if we forced entity B into the frame beforehand? It was already in the frame at T0. Well, we could easily accelerate each of them at T0 to their required velocity and carry on as we have done. But this instantaneous acceleration is what makes this case non-inertial. It's just a math space exercise with solid math to go with it. The items in question are massless notions behaving so that mathematics can chart them. But what if they had mass and a history of motion moving northwards before T0? With our math space processor, we can easily see that entity B at T0 will remain in the frame. But what actually happens due to the obligations of inertia? At T0, the eastward charge of 20 kilometers per hour attached to entity B will be enhanced by the northwards persuasion of the frame's 10 kilometers per hour. It will therefore travel 22.36 kilometers per hour on an angle smaller than the angle for the 20 kilometer per hour exercise. Smaller angle. And therefore it will cycle in a time shorter than the non-inertial case we just looked at. Comparing inertial and non-inertial. We just inject the velocity here and it follows along, trying to maintain what this mathematic exercise is trying to incorporate into the system. Here we have a frame in motion and it has energy that must be given or accounted for due to the obligations of inertia. And so at T0, it finds itself off on an angle that's smaller than this, but it's faster as well, and the whole inertial computation is shorter, and we can see that the distance in space is different here. This tighter angle brings entity B into contact with the endpoint of the frame a little bit sooner than, therefore, in direct analysis of the y axis of space, it intercepts it at a lesser y point. Seeing this outcome, we ask, why don't we prefer this reflection solution? For it also doesn't equal the cycle time of the northwards episode. Of course, In this cross-axis case, we see the exercise obeying the obligations of inertia. And in the former cross-axis case, we simply loaded v and v into a non-inertial expression. Just happy to use those values. The related northwards exercise also loaded large V and small v to calculate the cycle time for it. That the cycle times are not the same is just par for the mathematical, or should we say, math space case. So we understand that with the frame's velocity constant, we can merely inject a concept of math and values for the entities, meaning high V and low V. We just say, they're 20, and then carry on with the analysis and get a reflection. We can add mass to them and then wonder what that inertial path must do then. It will be different because now the frame and the entity are bound at T0. And so the entity B, must reflect that in its inertial case if it finds a different angle to project down, and it finds itself under the influence of the frame. So it has a higher velocity. The inertial case produces a higher velocity. Extending our observations, we notice that in both cross-axis cases, inertial and non-inertial, we witness entity B leaving the corner of the frame, run to the outer edge like a bowling ball in a lane, and return to the same corner as the cycle was completed. But we also witness the spatial activity, which we must accept as a simple vector activity, and both mathematical calculations pivot on the space point at T0. T0 has a consequence in both cases. We should call the corner of the moving frame the apparent excursion route for entity B. And each one of these is an apparent excursion route as the frame moves up. The corner becomes the apparent excursion route. And the spatial point at T0 is the root of all valid mathematical processing. So we just simply saying, as the frame moves on and the corner thereof continues to move on, the actual root is the spatial point here. This helps us understand all of this activity. Seeing what happens, as it goes, it just simply moves out and back along this channel or this corridor. And we must remind ourselves that it was space points that were critical to resolving the inertial analysis performed in spatializing Galilean relativity. And it was there that we saw how a non-inertial case spatializes exactly like an inertial case. Spatially speaking, they both employ an identical template, though each produces different cycle times. And that is where a key insight concerning Michelson's assay was let. So just looking carefully at these two propositions, one following a mathematics that we understood from earlier, this one understanding an inertial mathematics which changes the dynamic of things, we can say both of them having a 20-kilometer velocity could in fact be mass entities. But we're exercising them in two distinctly different ways. One inertial and one non-inertial. But notice the template. The template is this angular. This is the template, an angular activity for both entities, or the high velocity entity. Now, we recall that Michelson reciprocated his assay, meaning he mathematically held the interferometer at rest, such that it put into play an apparent ether wind. This reciprocation did nothing fundamental to irritate his case, but it did obfuscate how his assay imputed inertia in improper ways. And a great deal of insight happens when we simply remove the reciprocation. So we've just made a reference to removing the reciprocation. Given this expansion needs to explore that idea a little more deeply, I'm going to take an aside here and insert a bit of an explanation on the concept of the reciprocation. Now, the idea, of course, is easy enough for us to break down, but let's start with a simple survey and it take us there quickly. So we're on a scooter, straight road, out in the desert, very calm, very still, no wind at all. We're on the scooter and going about 20 kilometers per hour. We put our hand out with our palm facing forward, and we feel a bit of a pressure on our hand due to the fact that we're moving 20 kilometers per hour through an atmosphere that has mass to it, and so we feel this pressure. No problem. However, we stop the scooter and we notice ahead of us there's a storm cloud coming. Well, as we have stopped the scooter, we found that there was no breeze at all, nothing. There was nothing to add anything to the simple fact that we had been traveling at 20 kilometers per hour and felt only this one pressure based on the simple still density of the atmosphere. However, now that we've stopped and we see this storm coming, we see shortly that this nice strong breeze accompanies all of this. And sure enough, we hold our hand out as we sit there on the road and we feel now a pressure on our hand. And in fact, it's a 20 kilometer per hour wind and we feel exactly the same pressure. So simply enough, we have seen a scenario that from the perspective of the pressure on your hand, neither one makes that big a difference. They're very distinctive, and for many reasons, it's very important that one be defined correctly as opposed to the other when the circumstance requires it. But that's just two alternates on the same idea, with the focus being that the pressure on your hand is the same in either circumstance. Well, now let's do this. Let's remove the storm. We get back on the scooter on a very, very calm day still, and we get ourselves going again to 20 kilometers per hour, and we feel the breeze or the pressure on our hand, same as before. But now in our mind's eye, we reciprocate the problem, meaning we presume that what's important is the wind coming by us, as we presume, as it were, to be, well, still. We're fixed, and there's an apparent wind blowing past us. That's a reciprocation of the idea that we first looked at, where we presumed we were moving, and the still air still had an effect on our hand, a very specific pressure on our palm, and now we're looking at it reciprocated. We have we have considered ourselves at rest, and the wind that we experience, which is exactly the same as before, in the first state of this discussion. Well, now we have simply reciprocated the issue or the idea or the concept or the structure of what we have just set up here. If we take the reciprocation away, of course, now we realize we're the thing moving, and the atmosphere around us is fixed, and we still feel exactly the same pressure, given we have just taken ourselves out of the reciprocation. Well, Michelson's idea was to do exactly the same thing. He considered himself basically at rest. That's why you see in all of his early scenarios describing his experiment an apparent ether wind. We just experienced where an apparent ether wind would come from. Anything moving in the context of some substrate, substance, gas, whatever, there's going to be a relative, indexable relative motion to that substance or substrate. So, yes, there's always an apparent something that can be considered the thing moving. For Michelson, that reciprocation did nothing to alter his assay per se. Just as the pressure on the hand was the same under all the circumstances, so would Michelson's math for this particular problem as he's trying to build this interferometer. Certainly he knew the Earth was moving, but he could reciprocate the problem just for one single idea to be clear, which is he could sit there and presume that as he sat behind his source and fired the photons straight away from him, they would, as in all other Galilean relative rest scenarios, go straight through the splitter at a given point, go straight on down the path, as it were, hit a reflecting mirror, and come back straight to that exact point on the splitter. So through the splitter at P1, hit the reflection wall by going straight away, and then return. This was his reciprocated assay. You can simply see it that way. And so now let's look at this animation that gives us pretty much that exact idea. We're going to sort of move into the scenario and watch what happens. So there, we've just gone through P1. We're going straight away now. See, we're sitting behind the source and we're watching it go straight away to the P1 and then back. We can manually do it now. So right here, we hit P1. There's P1 on the splitter. It follows L straight away to the reflecting mirror. And this, as you see, is the incident that we will call as we go the inertial drag that Michelson would see his system to be performing. Now, truthfully, he did not see it as drag or anything else. He just was compensating for the idea that this in the ether is where light will travel at c. That's why in his math, the large V is c. It means this is moving at c. And it will continue on and return. Again, right back to P1, which is just occluded here, but we understand that's where it's going to hit because it stayed on the same track all the way and there and back. But see, this, as the ether wind is moving, the apparent ether wind, so to speak, is moving, we see it. See the bands here? That's the representation of the moving ether wind. The moving ether wind, we're fixed. We don't see any understanding of motion for the frame here. And there goes the photon reflected at this point out of the system. Later we will call this the y-axis as it exits the system. But this is Michelson's concern. This V path is what his math is trying to compensate for. He understands that. That is the path of the photon in space, cutting, as it were, this angular path through space and then back. But of course, the internal dynamic of him saying this is at rest is for him to see that the photon, if the source is down here somewhere, it's going to go straight away, straight to the mirror, and straight back. See, that's the local interpretation of things as he considers himself at rest. Now, almost anyone in the world would realize that this is a vector path. This is a vector path. But what vectorization is in the photon to keep it traveling along this path? Because it is technically going, see this path as it goes straight away and back, straight away and back? Well, it's having to fight this wind with some sort of vectorization component. Where does that come from? Well, Michelson's math certainly shows us that this path that we're looking at there and back is a slowed path compared to, let's say, if this whole system were totally at rest and there's no apparent ether wind to fight. This is going there and back, slower than C. This is a sub-C path. This is the sub-C path. This is the C path. And the difference is what shows up in his math. The greater time, as it were, the additional time, it were, for the photon to take this basically as a heading, and all of this is bearing, so to speak. But that is his concept of a reciprocated experiment. His assay allows him to not worry about whether it's reciprocated or not. He's just able to use that reciprocation to understand that the photon is going straight here and straight back. That's the value of his reciprocation, nothing else. He already knows by the math that this is going to be taking this longer path creates a longer time that is in fact downshifted, as it were, in the schema of the concept. It'll be downshifted here to a slower path here and back. But that's just it. It will go to the mirror and return to P1. And then, given it's a half-silvered mirror, many of the photons will reflect straight out, and then, as we say, travel along Y. Now we're going to do the same thing that we did a second ago with the scooter. We're going to now take the reciprocation away, and we're going to see, notice the frame moving with respect, here's the frame moving with respect to this background now that's not. We are fixed with the what were once moving lines as a reference, and we're seeing all the elements of the frame move. This is the true in situ state of the experiment as it sits in Michelson's basement. Of course it is. The frame is the thing moving. So we have taken his reciprocation away. However, we still get the same outcome, as it were, and we see again, it's not exactly the same V through space here. We've changed things only a slightly bit, but we see the V being carved, and this is what it does, and this is what it has to do. There's P1. It goes downrange, hits the reflecting mirror, and then returns. And again, we will say that it is at P1 again when it returns from the backside here. We've also see the on axis and back. So that's that one. But as we will see, the rest of his reciprocation removed, we still see his idea. We see that the photons come out one ahead of the other, given that this is actually a shorter path. But that's the reciprocation removed. This is the actual reality of the experiment that Michelson performed in his lab. And this again, when we remove the reciprocation, as we will continue to describe in slightly different terms, we will see that this path is very suspicious because we have no idea how to say that that inertia, that lateral inertia, had to be there all the way back from its emission from the source. We pick it up here, but we have to presume there's some lateral inertia that's kept it, as we were saying, in front of the source all the way through the exercise. That's because the source is pointed right at P1. It went through P1, and now with reciprocation removed, we see that this angle very much requires what we mentioned earlier, some sort of vectorization dynamic to put it on this path. It should, as we will explore later, it should behave in a much more specific non-inertial manner. But there's the explanation of removing the reciprocation, what it actually meant. It had no real problem in his assay, except that it masks this particular issue, that it has to very definitely follow some lateral inertia to keep it on this path that has it separate or penetrate at P1 on this splitter, and then as the splitter moves, it returns to P1, and it can only do that if it has some jog downrange, and it's the longer distance, but it's the lateral inertia component that's the big question. We take away the reciprocation, and we see this becomes in high relief, the fact that to leave and return, or to penetrate at P1 and then to return to P1 takes something that has to be called lateral inertia, and yet that inertia, as we've looked at closely in the previous discussion of inertial mathematics, it comes from nowhere and adds no proper amount of inertial dynamic, meaning it doesn't increase the speed as it should so, from the fact that the source should be adding something of speed, but it can't because light has a constant speed by virtue of all previous analysis. And so there, we see reciprocation. We see Michelson needing his photon to penetrate at P1 and then return to P1. And for that, there has to be some deflection angle, some lateral inertia, something that sort of comes from nowhere and is accounted for nowhere. All we see that he sees that it should take more time for this longer path, because this again is longer than the straight L back and forth. This V is a longer path. This he's accounting for as an extended time. And then Michelson's final dynamic is to have one behind the other, this one having the shorter path. Reciprocation removed, we can see the literal truth of his experimental situation. His apparatus was in motion through a putatively fixed space, and, shall we say, a space imbued with an ether. That was his objective, to deductively reduce a solution that upholds a strength for the idea of an ether. Under a schema where the frame is moving and the space is fixed, we see deeper into his assay. And this will be the important argument. Now we have reviewed a case where entity B followed both an inertial and non-inertial path with respect to a frame identical to Michelson's apparatus. But what we did not ask is what happens when entity B enters the scenario at T0 with a history of its own, meaning it is traveling eastward as it encounters the corner of the frame at T0. Assuming entity B is massless, i.e. a non-inertial entity, what deflects it to follow the non-inertial path as the non-inertial case presented above? If you are saying to yourself, probably nothing, you are right. But that is exactly what Michelson's assay requires. Notice this is the non-inertial behavior, but look at the template it is following. Same numbers, unaccelerated, a constant V as in the previous values that we looked at without the Radican, same values, V and small v. This is a schematic of Michelson's interferometer. Notice he is firing the source directly into the flow of the ether. Apparent ether coming in, source projecting. Now, to see our case most clearly, let's rotate it such that the source is firing across the flow of ether. Now it maps down to the case we have been presenting. We've been looking at a northward activity on the frame, so we have a southerly drift, as it were, and a southerly apparent ether wind. Now a photon is loosed from the source, and somehow the photon has acquired the lateral inertia of the frame. At least it must, to follow Michelson's assay. So it leaves the root emission in space, but pays homage to the moving source by flying directly away from it due to the lateral inertia it has somehow acquired. So spatialized, we see it leaving the spatial root and acquiring an angle that will allow it to pass through the splitter at P1, running along this angle until it is reflected, and finally returning to P1. Notice that at all times, the photon was directly in line with the source as it moved. This is Michelson's assay, and this expression computes the time it takes to leave P1 and return to it. But the alternate assay on offer cries foul. The source cannot imbue lateral inertia to the photon. If we believe that, then this expression is invalid. It is a non-inertial math, but it is fused into Michelson's misbegotten presumption of lateral inertia, creating the dynamic for the non-inertial math to describe. So this is the essential look of a lateral inertia case that must exist for this mathematics to have value, and yet we say it can't have lateral inertia. To state it most clearly, the photon must gain extra speed to vector laterally through space and appear to be fired straight away from the source. It must be influenced by the inertia of the source, meaning frame. But that would force an increase in speed as such a vector proposition would require. When you throw a ball out of a moving car, for a moment it seems to leave you at a given velocity, but to the ground it is moving from the point of release on a vectored angle which includes the speed of the car plus the speed of your thrust. And so it should go for the photon as it leaves the source. But the photon can't go faster than c. But Michelson blithely inserts c for the high velocity v, and in that sleight of hand stabilizes the scenario to become non-inertial. And that sleight of hand works on the fitful crowd because, of course, a photon can find itself on that path traveling at c. This is not restricted, but given the photon is traveling eastwards as it encounters the northward moving frame, what puts it on that path at P1? Lest it has improperly acquired, unaccounted for lateral inertia at its emission from the source. For the exercise, let's return to the very first scenario in this discussion and replace entity B with Michelson's source. The source fires a photon at a receding target. Here we see it, receding target. The photon enters space at c and runs down the target, which is traveling at small v, capital. We see simple open frame non-inertial activity. Now we attach the source to the base of the leg that is moving northwards. When the photon is fired, it enters space again at c. We accept this because we accept that the source does not add any of its velocity to the photon, and this is the heart of its non-inertial prescriptions. The photon then again runs down the receding target in exactly the same time as before, but we must accept that inherently it's separated from the source at less than c. We must accept this because the source's motion through space is as intractably real as the photon's motion. Yes, we currently accept that the source's operator perceives the photon to leave at c, but that can be repaired, just as Michelson's interferometer can be repaired with trivial procedures. So, all of this leaves us with the need to discuss this alternate assay, as we find that it may heal Michelson's punctured reasoning. And so, we can begin to speak to that healing with this scenario. A positron and an electron collide in space, out here somewhere, and the explosion sends a thin film, a bubble of radiation, out and away from itself in all directions. Very nice. We, however, take note of one particular photon that just travels straight away and finds itself on a perpendicular to our given frame we were just looking at, that's just moving northwards. Frame is moving northwards. And we see a splitter canted at 45 degrees lodged in the corner of the frame. And here comes the instant when the photon arrives at the splitter. As the photon passes through the splitter, we adhere to the photon's non-inertial qualities. We find that as the frame continues to move northwards, we can see clearly this photon doesn't know anything about that. And so we see the photon continue on, but the frame now is slipping away. It's moving northwards. It is behaving non-inertially in respect to the entanglement that occurred as it passed through the splitter. The frame continues moving on, and the photon continues moving on non-inertially. And because the frame is moving very slowly compared to the photon's speed, in just an instant it has reached the mirror and has been reflected back on its path. Well, again, it's going to take time to do all that, and the frame shall have moved on. And so, upon returning to the splitter, the photon will not strike P1. It is returned to the splitter, but P1 is here. Here's where the return finds it. P1 was host to a different episode at a different point in time. We see the photon striking P2. This would be P2. And at P2, it will reflect out of the system. And this again is the uppermost consequence that anchors this alternate assay. This is actually trying to happen in Michelson's interferometer every day all over the world. So here we see the true non-inertial behavior of a single photon going along at C. It is reflected and returns at C. And now it finds itself able to reflect away from the splitter and head away at 90 degrees angle to its crossing path. It shall exit the mirror maze here. As noted earlier, the equation Michelson used in his assay regulating the northwards leg of the frame can properly exhibit a correct non-inertial computation, and therefore describes light's non-inertial behavior, even as taken in the context of a moving inertial frame. He asked the photon to depart at C, and it does, but little regard is given to the fact that it leaves the source at the appropriate sub-C drift. But our recasting of the cross-axis activity shows that merely inserting a radicand at the proper spot in the same equation will not describe light's non-inertial behavior. By spatializing the activity, we see that Michelson prescribes an inertial template, asking the photon to veer downrange to sync with the frame. Again, we accept that a non-inertial path can follow that prescription, but we are strongly suspicious of how, when we see the frame in motion through a fixed ether, the photon magically finds itself on that path. Again, lest it acquire some lateral inertia from the source, and that seems very troublesome. So we see that a different math expression or sequence is required to describe a simple non-inertial path of a photon through the system. And here we must simply say that several papers attached to this alternate assay have developed in detail the accommodation sequence which describes the true non-inertial path. And so, though we can generally accept that Michelson's northwards expression is valid in its non-inertial resolution, we find it still suffers from not extending the computation to include the non-inertial activity of a non-inertial cross-axis option. It tracks the photon's behavior correctly up to a point, i.e., when the photon returns to P1 after reflection. To see the global structure, we must track the on-axis photon beyond that point, and a most satisfying consequence comes to us from the improved picture prescribed by the accommodation sequence. Here's the on-axis path. When we recast Michelson's assay, we see that the photons strike the splitter at different times, just as Michelson predicted. But the instant that both photons exit the mirror maze under this alternate assay, we find them side by side, not as Michelson's assay would have it, one behind the other. And yes, Michelson would have this one behind this one, technically this one behind that one. And should the freshly exited photons find their way downrange to a screen, they would strike it at exactly the same instant. They are, in a manner of speaking, time-aligned and or in phase. Now, if we take careful note, we see the photons exhibit the gap Michelson was searching for. We simply see it expressed on a different axis. And so we see that Michelson's interferometer would certainly produce a gap, but we must anticipate that more than Earth's motion through space will be layered into the gap. This alternate assay presumes to be sensitive to all motion incumbent on the frame. As a convenience, we can say that Michelson's assay predicts the gap will be on the y-axis. As it were, this is the y-axis. And this alternate assay, featuring the accommodation sequence and true non-inertial activity, predicts the gap to lie on the x-axis. As it strikes P2, it's further down range. It has passed the axis of the y along which the on-axis photon is traveling, and it strikes it here and will exit side by side. So we come to notes on reworking Michelson's interferometer. We ask, what would get rid of this all-important gap? Clearly history has shown it to not be in evidence. Enter Fitzgerald's contractions, but that discussion has been done. We see that Michelson's assay required reflecting mirrors set at 90 degrees to one another, and certainly so does the accommodation sequence. The problem very simply lies with Michelson's assay allowing him to think the mirrors would be set at 90 degrees if he tunes the beams to one spot on the screen. In that moment, he closes the gap that is, in fact, trying to express itself on the x-axis. For Michelson, tuning the reflecting mirrors to 90 degrees would have been one of his biggest technical challenges, but his assay sent him astray. In a modern context, we could simply CNC an ingot to have 90-degree faces and go from there. No tuning should be possible on the corrected apparatus. And since the corrected apparatus would be sensitive to all motions incumbent upon it, we can't predict the size of the gap, only that it should be there, expressed as 2 points on the screen. Indeed, it would take several years of data collection, as Michelson also anticipated, for a proper picture to emerge. So there it is. We have produced a topical survey that takes us from simple math-based problems to correcting Michelson's assay and interferometer. I feel it would be hard for a pure mathematician to reject this alternate assay out of hand. It is a purely mathematical conjecture with properly coherent strictures in place. It is not complicated enough to befuddle anyone. In summary, we find Earth to be moving through space, and Michelson interferometer should be cognizant of that. Removing the reciprocation is an easy adjustment. Indeed, very simple corrections to it would have it reflecting that truth. By reviewing the construct of Galilean relativity in spatializing Galilean relativity, we found the proper formation of an inertial template for cross-axis activity. We then note that Michelson's insertion of non-inertial math into an inertial template can be seen as valid, but suffers from the absence of a motive operator to fulfill the non-inertial prescription. There is nothing to deflect a photon to chase a mirror sliding downrange. lest you attach lateral inertia to a massless entity. We do not do that to stars in the distance. Michelson's assay has faults. The continuing error it produces in modern times is it allows the mirrors to be tuned to a single spot, anticipating a gap on the y-axis. This literally closes a gap on the x-axis that is inherently time-aligned, so nothing of a gap appears at the collector. He squeezes the gap out of existence by tuning the mirrors to a single spot. Thank you. Having the main block of the expansion behind us, it would be proper to add a summary of a sort to just clarify a few details that were, in fact, parsed very carefully with a lot of open-endedness in them because we're trying to attack this from a pure mathematical argument and then process as many of the logic steps that could apply, and sometimes we ask should apply to the different components. Clearly, we looked carefully at how this mathematical episode and this mathematical episode reduces to this and larger mathematical equations, looking at a total cycle time. We made a serious effort to show that this, while purely mathematical, it lends itself more truly to a non-inertial analysis. Even though this looks vectorish in a way, we're just injecting values here that play out in this form. So this V processes through, and this V processes through. And so there's no, it's only in a mathematical sense that blends the two episodes do we get this final equation. We call it non-inertial because indeed, previous to the expansion, we wrote a paper spatializing inertial mathematics where we looked at how this isn't necessarily an inertial case. In fact, it labors to be called an inertial case. And yet, it projects in spatial terms this kind of episode, this kind of spatial analysis. And so, what I wanted to do here is add one interesting point, and we can do it with this. If I move this frame to this instant point of explosion where the positron and the electron collide, and we see the frame here, for example. So the explosion happens in the corner of this frame. Well, do you see this outer boundary of the blast wave represents the infinite number of angles that can go off from this point, all of which are leaving at C. So no problem. When Michelson presents us with this sort of proposition coming from his mathematics, we're not necessarily alarmed. Certainly, light can follow this path, as we just saw. If we put the frame right on top of the explosion, we see that the sphere expanded away from it are all of the rays that could leave into that frame. And then we labored a bit on asking which question applies where, what should be the objective of any such crossing ray to find its way to a reflection, because there would be a great number of reflections available, or reflection angles, as we're saying. In other words, this has a lot of openness to it. It's a vector, but it can be a vector in any direction, giving us any number of total reflections for a cycle. In other words, this cycle is the cycle under question as we examine Michelson. And we're trying to show that in this crossing analysis, the main thing is that when we looked here at this scenario, we saw what essentially Michelson's mathematics tends to obscure as an important and very possible route. He has us chasing that vector looking path, but a true non-inertial path looks like this in his frame. His frame moves on, and the photon, as it were, would cycle through and come back straight back on its path. And in fact, as we noted, it would it would collide at a different point on the splitter as the splitter and frame move away. So we're making a big point about this particular component. This is the component where for Michelson to have his path, for Michelson to have this, it breaks down in real, in situ, when we know the Earth is moving through space, and let's just say space is fixed, and we're proposing that the ether, as Einstein liked to say at Leiden in 1920, it's unthinkable to not have an ether for his model of special relativity, or general relativity, as it were, in 1920. But this is what we're talking about. This is Michelson's path that the photon must follow. And we've just asked many times, how does this photon acquire any lateral inertia as it's emitted? You see, we're trying to make the strong case that a photon has a relationship with the ether or slash space, if you don't like the ether concept at all, but it has less so of a relationship with the source. They are merely entangled at a given instant in an episode where the photon has no real inertia. Now, again, let's not forget, we just looked at this. So clearly, this path is possible, as we see, this is the photon. And of course, all of other potential paths are open, as we see all these possible rays. And so Michelson's path is here somewhere, but we don't understand how, if it's this scenario, how we get any lateral inertia in the system. In other words, there's no lateral inertia in this burst. In fact, there's no lateral inertia in any of these photons. This is I suppose, one of the reasons for this summary, to just reiterate that you can see this, and you can see Michelson's path anywhere you'd like, especially his famous using the same numbers, large V and small v. But you have to see that none of this is inertial. All of these paths are non-inertial. But when we move the Earth, as we should, through a fixed field, ether, space, whatever, we find ourselves having to accept this formula with this outcome for it to go through P1, return to P1, and satisfy this particular mathematics. And we just found that very troublesome. This should not have this particular photon, as we saw on the positron and electron collision. This one has no inertia as it comes this way. It has none. We have a path open to go this way, but what, and again, the question goes over and over again, what puts it on that path? You see? Because the source is literally generated over here. So somehow a photon has to come here. It just, the angulation doesn't work. All we should see from this is that it goes straight away, as we see this little block move straight away. Well, that's what we were trying to attend with the positron scenario, and then return on its, of course, a very short frame in terms of all the speed of this photon allows us to then see that when it returns to a different point on the splitter. You see, it has returned and hit here. It went through at P1 as P1 was here, but then it returned, and the splitter and P1 have moved on, so he hit the splitter at a different point. And that's the root of the non-inertial assay we're trying to make. There's a lot of smaller sides here that can be expanded on, but this is the main point. Michelson did not seem to consider this proposition. He liked the math he used. It looked good. Most of the sages of his time could not see a real problem with his application of his maths. And so everyone was stymied until Fitzgerald came along and shrank the frame with a whole new empiricism and bring down a proposition that says maybe things shrink along their axis of motion. Well, we know that coefficients of heat change metals. And I mean, in the background of his thinking, there are examples. He's just applying a corollary, an analog to something like the coefficient of expansion uh, to this argument, and just shrinking the frame because of larger material issues that are just, well, accepted as shrinking the frame as it moves along that axis. It's an easy thing to digest and then continue to apply, but it's hard on the head when you think about it. So again, final survey that we are trying to make here is that this is pulled out of a Gamau's very excellent book. Its title has changed a couple of times, but extracting this page, we see this is Michelson's cross-axis analysis, and we see exactly what we've seen a second ago. 2L divided by V under the square root of 1 minus V squared over large V squared. This, of course, in Einstein's utility becomes U squared over C squared. So Einstein is just following this literal argument, has put together operators in special relativity based literally off of this activity. And as we would say, as U increases, meaning as this frame increases, this path increases, as we looked at earlier. And as you go faster and faster, see this path is represents speed along a different speed along a fixed frame rate. But if the frame rate goes faster and faster, then this whole math changes to give you a higher and tighter proposition for reflection. And so it takes longer and longer and longer for that reflection cycle to occur. As this goes up, the reflection cycle increases, period. And this is what Einstein's literal argument for the expansion of time is built on. Literally. It is the time it takes for a faster moving frame or something. And again, we have no idea how in his model anything follows this path, given it is injected from some out source, as it would be from an interferometer. It has to, just like we say in the positron example, there's just one path that satisfies it, and off it goes. It's not the way physics would work, in my opinion. You'd have to for his argument to have value, it would have to be a positron electron collision happening every instant that there is an analysis to be done. Okay, maybe so, maybe there is, but I think not. His argument merely uses the same out of nowhere lateral inertia, a deflection in the system that comes from no real place. But once you track with the math, if you just force the math into it, if you force the math to regulate the path, which is what I'm trying to say, the math regulates the path, and that's all that's of concern. Yes, light can follow that path. It would have to be a positron electron collision sending rays every direction for that particular path to appear. Any single photon coming in from an out source coming into the system, as we think that's what Michelson's interferometer is really doing, is sending a photon in from an out source, though the source is part of the frame. We find no lateral inertia to be imbued in that release of a photon. And so the photon enters free space. It enters the ether with no lateral inertia and then just goes straight away and straight back. again at its one value of C, which is very happy. Was very happy to satisfy so many more logic points. Is that we see no confusion about how a vector path may or may not appear. And so these are some of the collected notes that I think should follow this expansion. We're looking at a probability as I see it anymore. It was just a rogue mathematical possibility long ago, but so many pieces of the math that we're breaking apart here show us that there's something to pursue, and pursue meaning actually accept some of these component thoughts and reprocess the whole case. As I've said, it would be easy to fix Michelson's interferometer. All you have to do is make sure before you start that you have mirrors at 90 degrees. Of course, I wouldn't put mirrors in any case. I would use an ingot. I would fix it literally and just do all this on a micro scale with micro lasers and a thermally balanced ingot that we carve out a 90 on. And of course, we'd have to get rid of errata. We'd have to carve many of these ingots from different CNC systems to just find out what the averaging of errata is at this level. But understanding that we're trying to start implacably with 90-degree angles and faces, we don't do any of Michelson's tuning. That's his main technical error. Of course, it's not an error with respect to his assay. His assay allows him to do it, but we're trying to break through all of his assay and show that you can't tune the mirrors as blithely as he thought he could to get his system lined up, because again, his assay expected exactly this. He expected one of these photons to be behind the other, and of course this is properly shown to be overlain here, one behind the other in the y-axis. We have seen that in a truly non-inertial case, P1 could be incident 1, but after motion of the frame, and again this sort of shows what we would actually like to see, a return, we don't have P1 anymore. We have P2, and it's reflecting out way over here, as it were, just as an exaggeration, and exiting way over here. So this is an inferential. It's just trying to illustrate the thing, but the truth is that little x is what we're looking for in this scenario. That gap isn't supposed to be there. It's supposed to hit P1, return to P1, and come straight back. This just gives you a clearer graphic, but it's also for us, it's approximating the correctness that a true non-inertial case would present. This would be wider, as it were, or as wide as the motion would produce. We close this summary just saying that there's many of these pieces have been worked very carefully and I think correctly, but they present sort of a sprawling case. Sadly, this does not reduce down to a single mathematical equation. This is a this is a reduction. This is an analytical reduction that takes into account many options simultaneously, and we just use what we think are the best indicators to find a way forward, some of which are simple, some of which are even remedial, but some of which catch us out, and we have to accept that perhaps we need to re-examine this case along the lines we have tried to chart here. So, thank you.